So let's go over the agenda and the assignment for next time. We'll be wrapping up chapter 7 today. The last major topic is called similitude, which is how I can do an experiment with a fraction 100 times less in a model test versus that of testing a prototype. How do I make sure that my testing in a much lower budget will give me data that is useful? So that's what we started as a motivation for this chapter of dimensional analysis. So we went through all the pi term. Now the rubber meets the road. And that is, how can I take further advantage of that to do a cheap, inexpensive experiment and make sure the data from my wind tunnel can be used to extrapolate to an actual full-size Boeing 787 Dreamliner. We do that by example because it's a little, again, vague. An example will help to bring all the pieces together. That should take about the first 20 minutes of the lecture, and then I will touch on the two homework today, the pump and the pipe flow. Then I will spend a little time on the new homework just to set you up. That has to do with model testing. Whatever left, we want to wrap up Bernoulli, which I didn't have time to cover last time, and it's a very simple problem of a water jet driven by gravity. And also touch on the cavitation problem and the last homework that I didn't have time to do last lecture. If time permits, I will start chapter 8, which is flow in the pipe, looking at more exactly the Moody diagram, how one determines the friction factor, and how it may relate to what we have done in chapter 7. So that's the full agenda for today. Just a note, tomorrow my office hours change to the morning, so if you plan to see me, please take a note of that. On the left is the assignment. Chapter 7, we are finishing the reading. You find section there has to do with additional pi term, typically found in fluid mechanics. We have only touched on a few, 2 or 3. Reynolds number, pressure coefficient, drag coefficient, but there are at least a dozen more. And it's up to you to kind of read them and get a sense of what they are and how they come about. And then the last section has to do with similitude experimentation, model testing specifically. So assignments look different. There are 3 problems just like we normally do. But what I would like from you, in addition to that, is a half-page type feedback from me and Mike on how you would like improvement to be made for the second half of the semester. If you look at the calendar, we are exactly at the halfway point. Yep, no joke. If you count Thanksgiving, have no classes. We are, in terms of lecture, 50% of lecture is gone. So we like to have some written feedback instead of scan type multiple choice. I want to have you be specific and tell us area of improvement. Does that make sense? It will be counted as a homework. It will be collected. It will be graded by me. And anyone who turned it in will get a 10 unless you didn't type that. Then you get a 5. How's that? You don't send that assignment? Yeah, half page because I just don't want to spend and give me a 3-page write-up. It's not needed. Just be very high level and say whatever you want to improve for the remaining of the semester. And then the assignment for a week from today, we'll talk about that. So any question before I start? So a high-level recap is shown there. We will refer to that throughout this lecture. So pipe flow, we went through a lot of solid and dense, come up with a pi term. And now I hope you're all very comfortable to what is called a pressure coefficient. Any question on that? Dimensionless, half rho v squared, the 1/2 is not from dimensional analysis, it's from convention. Right? And it's a function of Reynolds number, length to diameter, roughness. That's the Moody diagram. But how this function comes about is, as you have done the homework due today, by experiment. That's the only way. Dimensional analysis is not going to tell you what is the pressure drop, how does it behave, how then is a function of. What function? I have no clue whatsoever. Got it? So we are, in this lecture, talk about what kind of experiment you can do. How do I do experiment in water and get same data, same behavior, same physics as there is in air? Then we talk about loosely external flow, an airfoil is just one. It could be a spear. And we talk about drag force, but it could easily be the lift, any force, right? And we formulated the dimensional analysis. We now have what we call a drag or force coefficient, can be drag coefficient, can be lift coefficient. And we see how it comes about by inspection. No more wasting opponent A, B, C and do a three unknown type problem. And then that's purely a function of Reynolds number. Any question on those? Big picture, 30,000 feet looking down. So we're going to build on this. And the first example that I call similitude relate to the second example, the airfoil problem that we went through last time. Similitude, similarity. How can I do a model test 100 times the size, 100? And do it in air and get some useful data that I can extrapolate to a prototype. And in a very loose sense, sense, how do I ensure my experiment is giving me useful data? So let's set up the example and use that to illustrate what we meant by similitude. So we're going to look at a blimp, an airship like Hindenburg, or the one that you see in the NFL Monday night game, right? And those things are huge, big. And what I want to know, as an aerodynamic engineer, is given this size of an airship, about half the football field, in air, hovering or moving very slowly in air, at 20 degrees centigrade. And here's the observation tower with a propeller that guides the ship cruise at relatively low speed. How low? Let's say 6 meters per second. But it's moving. I want to find, for this what I call prototype, that's the actual machine. The full size rim. I simply want to know at that speed of 6 meters per second in air, what's the drag? By knowing the drag, then I can estimate how big the motor, in terms of the power, required to drive this propeller to maintain that constant speed of 6 meters per second. That's the problem statement. And you can extend that to a 787, the Boeing Dreamliner, full-size aircraft. I want to know the drag at 250 miles per hour at 30,000 feet. Well, the simple answer is build one, test it. If it crashes, build another one. Right? It's not possible. Cost prohibitive. So someone suggested, hey, how about if we test a model in water? Not in air, but in water. The model is going to be 1/30th, 30 times smaller than the prototype, but it looks exactly the same. We call geometric similitude. In other words, it will be like taking a picture of the prototype on your iPhone and then you keep shrinking it by 30 times, and you look exactly the same. All the details, okay? All the small pieces. The model will be represented. For that, my question is, for this smaller model, which is 1/30th the size, in water, what velocity I should test it in my water tunnel? So in a wind tunnel, water tunnel, usually the model is stationary. is mounted on what is called a sting, which is nothing but a support. But the fluid is moving. So in the water tunnel, the water is washing through in the tunnel towards that model at a speed that yet to be determined. In the wind tunnel, we have outside raindrops, the same. An airplane model will be stationary, but the air is moving. So relative to the model, it's the same physics. Do you understand the relative velocity transformation? Okay, so it's the same setup. Question first and foremost is, what speed I should run my water tunnel? And after that, if at this speed, I measure my model drag force, at this speed that is to be determined, I measure the drag force to be 2,700 Newton. How do I take that experimental data and hope to infer for this 30 times bigger airship at 6 meters per second in air, not in water, in air? What would that force be? What would that drag force be? And if I can do that, you can see the amount of saving I can have in determining the best shape, aerodynamic shape for this type of airship. Because I can start changing things to make it more efficient, less drag, and keep testing it until I have the best geometric shape. And then I'm going to build it, which will cost me a lot of money, but I won't do it once. I do all my iterations in a much cheaper experiment. That's what we're after. Yes?
Why are we testing it in water, not in air?
That's a question I'd like you to answer next time, after you've done the homework. Those are very good questions. And the bottom line is, it turns out you don't always be able to match all those parameters due to physical constraints. What are they? I want you to find out by doing the homework. All homework will point to that direction. Okay? So let me finish the example and then you can hit home. There are only some problems like this one that allow you to have that kind of matching. In real life, the testing in a wind tunnel doesn't always get you the exact answer. Okay? And that's how engineers like us get burned. You assume your data in the wind tunnel is good, you build a prototype, whoa, you're off by 10%. It's usually in the wrong direction, meaning more drag. That's why you get job for you, is to fix those problems. Okay? Yes, there was a question about?
Why do we still need these physical experiments when we have software simulation?
Oh, that's $1 million question. Evan here, you have computer, you have something which we'll touch on called computational fluid dynamics, which is you set up the entire domain with the geometry of this prototype, and you put in a computer and spit out a number, which will tell you everything you want to know in the flow field, pressure, temperature, and the drag. But it turns out those simulations make a lot of assumptions. The most important of which is assuming some type of turbulence behavior, which we haven't touched yet. We will. So bottom line, those computational, those simulations is not exactly correct either. And that's why people have to do experiment. And they do this cheap experiment, try to cut costs, and then they do a one-time prototype and hope and pray that it works. And if it doesn't, let the engine hang in the hallway, it's a very expensive fix. Unbelievable. Because everything has been designed and fabricated, and now you're trying to fix it. It's very costly. Okay? So all those will be addressed in the next remaining of the semester, let's say. But those are very good questions that get us motivated. And for better for worse, that's how companies like Pratt & Whitney, the Boeing, the Lockheed Martin lead engineer like you. Because despite the fact it's a science, it's not a pure science. There's still a lot of guesswork, right? So, that is a motivation. Before I can dive in and solve that problem, let's re-examine what we meant by similitude, or how do I know my experiment in the water can give me meaningful result. So there are 3 similarity conditions we call similitude that must be met First is geometry. My 30th size model must look exactly the same as my prototype. So here's a very simple cartoon to illustrate that. So airfoil or brim, which is a teardrop shape. For the model, I have dimension D1 and D2. My prototype, which is considerably bigger, a D1 star and D2 star. By geometric similitude, all I'm referring to, if I take a picture of one and either enlarge it or shrink it, it will look exactly the same as the other. So geometric similitude in Word is that all the dimensions, width, length, depth, must be proportional to each other. Same ratio to each other. It sounds simple, right? I mean, what's the big deal? So take a 787 and string it 100 times and build all the detail. When your model is only 5 foot or even 3 feet in size, a lot of that detail cannot be truly and accurately reproduced. One of which, how about the surface roughness of those airfoil on an actual airplane? They are small, they may be in the actual size, micrometers, fraction of an inch, and when you string it down by 100 times, there's just no way you can reproduce those surface roughness. So that alone, obviously, is something you cannot match in the wind tunnel. All right? But you do the best you can, and this is the first and most easy, relatively, criteria to meet. Second, kinematic. Velocity, meaning no forces, just velocity field and acceleration field. We call it kinematic, now you learn in dynamic. Kinematic similitude. All the velocity and acceleration at each corresponding point between the model and the prototype. Stay in the same ratio. What does that mean to you? When I take a Boeing 787 and string it back by 100 times, it turns out the velocity has to also go, but not reduce by 100 times. That's your homework problem. You'll find that the velocity actually have to increase by 100 times. So how fast is the Boeing 787 flying? Airplane at 30,000 feet typically cruise at about 0.8 Mach number. What is the sea level speed of sound? 340 meters per second, 1,000 feet per second. At high atmosphere, is translated to, with the correction for pressure and temperature, typically 250 miles per hour. So increase that by 100 times. I have done your homework for you already. That's basically what you're asked to do for the homework. But why increase by 100 times? We'll get to that in a moment, all right? So velocity field, acceleration field has to match point by point. The last one is forces that we call dynamic similitude. forces F to the MA on all points must also stand in ratio to each other. How is where we will further illustrate by example and by the homework. So when I say full similitude, meaning that's where my model has will exactly reproduce the same physics, no more, no less, compared to my prototype. All three conditions, all three conditions of geometric, kinematic, and dynamic similitude are all matched. So all A, when I have all three conditions are met, A, B, and C, I can succeed in matching all three. It turns out it resulted in a very important consequences. And that is all the dimensionless pi terms, all the pi's that we have developed from dimensional analysis, like the pi flow, like the airfoil, all those perimeters must equal to each other. In other words, the pi term, choose one, Reynolds number, drag coefficient, relative roughness, on the condition that A, B, and C are met, all those pi terms must equal to each other. That's very powerful. And that's how we will use this to do model testing. Why is that? It's in your reading assignment. I won't go through that in detail, but the consequence of this is actually based on taking the equation of motion at this stage you only have seen one. Which one is that? Was the only differential equation of motion you have been exposed to up to this point? Differential equation of motion. Differential meaning small, tiny element of dx, dy, dz. You only seen one. Which one is that? You forgot? The Euler. The Euler. Which is the simplest one as the introduction. The consequence of why the pi term matches, if you take that equation of motion and Euler's and you non-dimensionalize it, which is given in detail in your textbook, what you find then is the equation can be cast in dimensionless terms like the Reynolds number and so forth. And from that non-dimensionalization, you will conclude that for physics to match, the pi term must equal. And that's what we use to solve this example problem. So I'm focusing more on the application than trying to show you the derivation of why this similitude, when A, B, C are met, all the pi term must equal. So that is something you can read on your own. So armed with that, let's see how we can do this example. Questions so far? So the first task is I have to decide, first and foremost, how to non-dimensionalize this problem, right? Because it didn't say anything about what should be the pi term. It's just all given in physical quantities. So what is the first step? What is the first step? You have to decide the pi term, right? Have we done that? When? When did we do that? How do you know the pi term for this airship? It's here. Which one will you use? What are the pi terms that would dictate the physics of this ellipsoid cutting through air? Say it again?
The airfoil.
The airfoil. Different shape, but same physics. And I'm after the drag force, which we have done last time, for that of an airfoil shape, but whether it's an airfoil, ellipsoid, or sphere, it's the same dimensional analysis, which we have done. And the answer is, I only have two pi terms. Pi 1 is a drag coefficient, pi 2 is the same old Reynolds number. Right? Do you get it? So what we have done in the last minute was those pi terms for that of the model must be exactly the same as that for the prototype. That's how I can relate the drag of the prototype. That's my ultimate experimental objective. But as an intermediate step, I have to determine how fast I need to run my water tunnel. And that's where the Reynolds number comes in. Yeah, we can test it in water. The viscosity and density will change. But as long as you match the Reynolds number, I don't care what fluid it is. Just like the pipe flow that we did in terms of using air, water, and oil as the media. I don't care, as long as you match those pi terms, Reynolds number, pressure drop coefficient, etc., etc. And that is the foundation of similitude or model testing. Do you get it? Yes?
So what are the M and P subscripts again?
Sure. Good clarification. All the subscript I use now, M stand for model, P stand for, anyone? Prototype. Yeah, that's the same nomenclature we'll use throughout the semester. Right, so I don't care it's air versus water, as long as the Reynolds number is matched, I have the same physics. The flow will behave exactly the same. Okay? So how do I determine the velocity of my water tunnel? Well, you match the Reynolds number, which is rho U length divided by the viscosity of the air versus that of water. The only unknown I have of which I would use the Reynolds number to determine is how fast I run my water tunnel. Right? The others are all property I can look up. The water test is also at room temperature, 20 degrees centigrade. So if you look up those properties, which I will give you in the unit of SI that's for air. It's nothing but a table lookup in the appendix. And for water, about 1,000 kilograms per meter cube. And the viscosity is several order of magnitude higher compared to air. So that's just a table lookup, and now I can do the numeric. This is one of the very few times that you don't have to carry the units in your calculation. And what I meant is The Reynolds number is shown in here. As long as both the unit on both sides are consistent, meaning in SI, you can skip the units. And you don't have to worry about dealing with G sub C. So the model size is 1/30th, and the only unknown left is now the model velocity u sub m. And again, I take the risk of not using the unit, but this is just a ratio, so I'm safe as long as I have same unit on both sides. Don't have to worry about factor of 1,000 or T sub c. So this simply tell me to match the Reynolds number, despite you are now in water, I simply have to run the water tunnel at 12 meters per second, which is very reasonable, quite doable. You just have a pump that is powerful enough to push the water in your water tunnel to get 12 meters per second. It's not too demanding. Yes?
So of the three types of similitudes that you listed over there,
Yeah.
A, B, and C, which of those are covered by equating the pi terms?
All of them.
All of them?
Yeah.
Okay.
The fact you have all three similitudes is to make sure your differential equation of motion are all cast in the same form. Then you non-dimensionalize it so that the equation have no units. In going through that, all the pi term will be matched and your hands are bound to have the same physics between the model and the prototype. Every pi term must be equivalent to each other between the model and the prototype. That's how that detail that I didn't cover. All right? Yes?
So if you were to have your same size prototype in air, you would have to operate at 180 meters per second?
The same size, wait a minute, the same size meaning if you take that 1/30th model and run it in air, yeah, then you just scale it according to the Reynolds number being matched.
So,
Both cases, yeah, but I don't understand why you would do that.
but is the point of using water so you don't have to operate it at a higher velocity?
No, so big picture, why do I do this experiment in water? If you do it in air, you have no choice but to build a full-size prototype. Right? Oh, I see what you're saying. Build a 1/30th model and do it in air? Yeah, you have to change the velocity, yeah. Yeah, correct. Yeah, you could have done it in air, yeah.
So then likewise, if you wanted to test something like a ship in water, would you
Mhm.
just choose something that's more viscous?
You
or-
could. You will find very quickly that there are a lot of limitations. This is but one out of thousands of examples that you can match those parameters relatively easier. Your homework, which involves an airplane, which I have explained, and also involve testing an automobile, smaller scale in a wind tunnel, we will find it's very difficult to match those dimensionless parameters. Because limitation of power or the fluid, you're not going to use some exotic fluid that's toxic. And turns out that there are many cases you don't match them. You couldn't because it's just too difficult. And your homework will illustrate why they are difficult. All right? There were another question? So this is somewhat of a unique case that it happened because of the low speed of that airship that I can manage to match those parameters with ease. It's not typical, by far, by any stretch. Testing an aircraft carrier in a water tunnel is never going to match everything. Testing a 787 in a wind tunnel here at Virginia Tech is never going to match the Reynolds number, and so on. Those are the assignments that you have found out. Okay? And then next time I give you some more exotic testing technique that's used by NASA, but it's also very expensive. Right? That's next time. So, what's the next step to get the projected or interpolated prototype force for this air beam in air? What would you do as the next step? Answer is, you equate what? You equate the next pi term, which is only one left. That's the drag coefficient. And again, because of the ratio, you can be sloppy and not carry the unit. So in order to get the drag force, I just equate the two drag coefficient. And knowing the length scale is 1/30, this resulted that in air, for that 30 times bigger model, it's about 730 Newton. And I have now the matching condition between my water test and my actual application in air. And lastly, to get the power. From the physics, power is force times what? Velocity? Yep, very good. Both of which I know. So it's about 7 kilowatt, which is reasonable, not too big, because you're not moving very fast. It's basically just a balloon. So for a very limited low-speed application, I managed to match all the pi terms. But again, I emphasize, your homework will show you it's not typical. Okay? Do you understand the concept of this similitude? Okay, very good. Let me touch on the two homework due today, of which I hope you have no problem doing them. The first one is the water pump. So, any question? Any question? You all have done it? So the answer, which I hope by inspection Massaji will get it. Right? Yes?
Would it have been incorrect to put a 1/2 in the denominator?
No. It's a very good question. The 1/2 is not from dimensional analysis. It's simply from convention. So you're more than welcome to put the 1/2 there. Right? This is similar to 1/2 rho v squared. So get used to looking at omega. It's the first time, but you will come back again. So omega times the length is equivalent to velocity, and that's how this term comes about. Questions? So if I put an extension to this homework, the original problem statements were delta P as a function of those 4 parameters, and you've done the problem 2 pi terms, right? So if I in the test, give you a third one. So we talked about last time, by neglecting viscosity, we are assuming the problem to be inviscid. The reason I did it is because it's simpler. Now I throw in viscosity. Can you immediately tell me by inspection how the answer will change? How many pi terms? Instead of 2? 3. What's the third one? What is the third? You have to think I failed. It's the Reynolds number. Anytime you see viscosity, without thinking, just spit out it's the Reynolds number. And how will the Reynolds number look like this time? Viscosity in the denominator, rho, a length scale, which is the diameter, that's the same as before. And how do I replace the velocity? Huh? D omega. Done. 2 seconds. Can you see that? So after you have a few homework, become more and more familiar. There's a unique set of engineering problem that always lend itself to the same pi terms, which Reynolds number is always there if you take into account viscosity, always. Okay? The pipe flow is a precursor to chapter 8. So the table you will make, and here's some solution of the CP. The x-axis is actually the Reynolds number. Yes,
Normally, when we talk about velocity, we say like r omega, not d omega.
that's fine.
So do you need to say like 1/2?
You can. So instead of diameter, you can arguably say, use the radius. Am I correct? Is that what you're asking?
Yes.
By all means. Have I changed anything in terms of dimensional analysis? No. No.
But that changes the numerical value.
It changes the numerical value. Well done and well said. Just like this 1/2. Right? Because now I have 2r in here. But remember, dimensional analysis never attempt to tell me what this function is. I have to do that by experiment. So whether it's 1/2 here, 2 here is inconsequential. Whether it's a function of Reynolds number or 1 over the Reynolds number, I don't care, as long as it's functional. How would the function behave? I have no clue. I have no way of knowing that from dimensional analysis. The only way I can do it is to go do an experiment. Just like you did for this problem. Is that detail well taken? I think I have repeated that at least 3 times, but it's very subtle. So chapter 7 had nothing to do with how pipe flow will lead to how much pressure drop. You can't do that from chapter 7. You can only do it from experiment. And that's chapter 8 and chapter 9. Right? But it's very powerful because we learned how I can simplify a problem by taking a 7 or 8 variable problem and reduce it by -3. Number 1. Number 2, I can now have a mean to do an experiment that have matching physics by matching the pi terms. That's it in chapter 7. No more, no less. Yep.
So just for clarification, when you're solving for your pi terms,
Uh-huh.
you pick like 3 different variables that the functions, you can't like take them, you know what I mean?
Yep.
Do those have to be on the right-hand side of the equation?
They always will be on the right-hand side of the equation. I don't have it. Yes, because you use the independent variables. 3 of them on the right-hand side to form those pi terms. And I have, after I went through this pi problem, I have a summary of how to do that one more time. But it is, as you said, it has to be on the right-hand side. Right. So this is a preview of what is to come for chapter 8. If you plot this data, it behaves like this. On the linear scale, where the Reynolds number, which is the essence of why I repeat this, is all but less than 2,000. So Reynolds number less than 2,000, we mentioned that last time. What type of flow you expect in the pipe? Laminar, and we'll touch on what that means. It's laminar, meaning that if you curve fit these 4 points, the relationship will show you is the reciprocal or the log of 1 over Reynolds number. So that if I plot this data on a log-log scale, log scale. Or Reynolds number. Six million, that will be a straight line. And the limitation, the range that it apply is Reynolds number small. How small? 2,000. All right, so that's just a good recap of dimensional, or rather of the Moody diagram, which is the next topic we'll talk about in chapter 8. But before I move all away from dimensional analysis, one revisit of how to pick those independent variables. Just a question asked before. How do I, now that I have several examples to build on, I'd like to do a revisit, big picture of how one, like you, will pick those three terms that are on the right-hand side, because they have to be independent variables. How do I pick those in order to form my pi term? So, example one is the pi flow, where our intuitions say those are the independent variables. The acceptable choice